Welcome back to The Deep Dive, the show where we take the hardest, most complex stack of information you've shared, strip out the noise, and hand you the core insights. Today, we are strapping ourselves in for a high-velocity look at one of the biggest computational rivalries happening right now. It's this high-stakes battle between traditional physics-based weather forecasting and the new hyper-efficient machine learning models.
It's truly a high-stakes frontier. And, we're talking about disrupting a system that has been refined for, well, over half a century. Historically, forecasting has been defined by just brute computational force. The models we're talking about, the traditional ones, are centered on what we call numerical weather prediction.
Or NWP.
NWP, exactly.
Okay, so let's unpack this for the listener. They might be familiar with the term, but maybe not the sheer scale of the effort. When you say NWP, what are these systems, which, usually require the world's biggest supercomputers, actually doing?
Well, they're essentially running an immense continuous physics simulation of the entire global atmosphere. At its heart, NWP is solving a massive, complex set of equations, specifically partial differential equations.
Right, PDEs.
PDEs. And these aren't just approximations. These equations are derived directly from the fundamental laws of physics, the conservation of momentum, mass, and energy.
So if you remember your high school physics, it's those foundational rules, but they're being applied to every cubic meter of air on the entire planet all at the same time.
Precisely. They mathematically describe how every bit of air, every molecule of water vapor responds to pressure, to temperature changes, and the Earth's rotation across the globe. The outcome has been these incredibly precise forecasts, and for decades, the undisputed global gold standard has been systems like the European Center for Medium-Range Weather Forecasts.
The ECMWF.
Yes, their integrated forecasting system, the IFS. They have, for a long time, set the bar for operational accuracy.
And their success is why they've also established the bar for computational cost. It's enormous. But now we have the AI challenge. Suddenly, these brand new, fully data-driven models, which essentially just ignore that classical method of solving PDEs, are routinely claiming they have superior performance. Our sources are highlighting models like GraphCast, Pangu-Weather, GenCast, FCM3. All of them are saying they can beat the best that physics has to offer.
And do it orders of magnitude faster.
Right.
And that is the core conflict we have to analyze today. We aren't here to just cheer for the fastest machine. Our mission is to synthesize the recent research on these kilometer scale and global AI weather models, what we call MLWP, machine learning weather prediction.
Okay.
We need to establish exactly where they're getting their unparalleled efficiency and skill, but also, and this is critical, where the fundamental chaotic physics of the atmosphere still presents these huge roadblocks that a purely data-driven approach just might not be able to overcome.
So it sounds like we're going on a journey from a massive supercomputer rack right to the heart of the butterfly effect. Let's start with the one advantage that is just undeniable, this radical shift in computational cost. Looking at the documents you've provided, the cost comparison is, like you said, it's staggering. When we look at traditional NWP, we are talking about operations that require thousands of CPU hours.
Thousands. Just to run a single forecast cycle.
So why is that specific iterative physics calculation so computationally expensive when you do it at scale?
It's the sheer volume of arithmetic that's required and the iterative nature of the solution. Imagine the atmosphere is divided into billions of tiny virtual boxes. Those are the grid points. At every single prediction step, which might only be a few minutes in real time, the model has to calculate the physics, the wind, temperature, pressure, humidity, at every single one of those locations.
And not just on the ground, but all the way up.
All the way up, across multiple vertical levels. And then it has to use that new state to calculate the next step and the next and so on.
It's a continuous, simultaneous calculation. It never stops.
Exactly. For a global medium-range forecast, they might be tracking 6 core atmospheric variables, but repeated across 37 different pressure levels deep into the atmosphere. So even if the physics calculation for one point is fast, you multiply that by the entire atmosphere, 37 levels deep, thousands of times over, to get to a 10-day forecast.
It becomes computationally prohibitive for anyone outside a major government lab.
Exactly. You just can't do it.
And that's where the machine learning weather prediction models come in with what feels like a fundamental change in the rules of the game. They just bypass that whole iterative PDE solving process.
They do. And the result is this massive efficiency game. Our sources confirm that once an AI model is trained, and that is the intensive part, the actual process of running the forecast, which we call inference, delivers results using dramatically less computing power.
How dramatically less are we talking about here? Can you give us a sense of scale?
We are talking about models running on a single modern GPU in just a few minutes.
A single GPU.
A single GPU. So when you compare this to the NWP systems running on massive supercomputers, the speedups reach up to 4 orders of magnitude.
4 orders of magnitude. That's not just a little faster. That's moving from needing a room full of specialized hardware to, what, a single workstation?
Potentially, yes. A single powerful workstation.
I have to ask, though, a speedup that massive sounds almost too good to be true. What's the hidden cost? Are they sacrificing resolution or accuracy? Where's the trade-off?
That's the critical, ongoing debate we'll get into later. But the initial trade-off is often focused on the training phase. Training these deep learning models requires access to decades of historical, high-quality weather data, often reanalysis data sets like ERA5, and a significant initial amount of compute power.
Right, the training is the heavy lift.
But even that intense training phase is getting faster and faster.
Can you give me an example of that speed?
Sure. Take an early model, ForecastNet. It was trained in about an hour on a supercomputer. Now, that's an intensive 60 minutes for sure. But once it's done, that model is ready to serve predictions. So its time to forecast ratio, when you look at it over the entire lifespan of the model, becomes thousands of times faster than continuously running these state-of-the-art physics models to get the same output.
So you front-load the cost, and then you reap these exponential benefits on inference.
Exactly.
And the resulting implication, which researchers are calling the democratization of weather prediction, is maybe the most compelling social change here. It changes who gets to access and use this powerful technology.
Absolutely. High-resolution global forecasting used to be the exclusive domain of major governmental agencies, billion-dollar research centers, simply because of the supercomputing demands.
Right.
Now that is rapidly shifting.
You included a really fascinating case study on this from San Diego State University. Tell us what they managed to accomplish.
That case study perfectly illustrates the shift. The researchers there, they leveraged readily available modern NVIDIA GPUs, specifically the A100 and L40 models.
So off-the-shelf, powerful hardware.
Exactly. And they used common infrastructure tools like Kubernetes and JupyterLab. With this setup, they could quickly deploy working environments for models like ForecastNet v2. And this is crucial. The ability to run these sophisticated simulations moves from requiring a national lab's budget to being accessible within a well-equipped university research lab.
Or even a specialized classroom.
Or even a classroom.
That's a huge academic leap. So now graduate and undergraduate students can actually practice operational numerical forecasting in their coursework. They can test hypotheses and run simulations that were, well, completely infeasible just 5 years ago.
It's opening the door to the next generation of meteorologists.
And beyond academia, you have to think about the powerful global societal impact.
Right.
I mean, if a national meteorological agency in a low or middle income country, which is often limited by infrastructure costs, can suddenly run a high-resolution global forecast in seconds on a single desktop computer, that immediately changes its capacity to serve its population.
It's a total game changer.
This moves way beyond simple scientific curiosity. This becomes a matter of economic stability.
It really does. We are talking about providing timely, localized predictions, especially for crucial variables like rainfall patterns. Farmers need this information to make critical, time-sensitive decisions about when to plant, when to harvest, or how much fertilizer to use. Without timely local forecasts, they're often operating on tradition or just luck.
So access to these timely, localized forecasts can lead directly to significantly better crop yields and lower costs.
Which directly addresses issues of food security and economic stability on a national scale. This is a direct line from computational speed to human benefit.
That makes the speed gain feel like an ethical imperative, not just a technological curiosity. But let's zoom in on how they achieve this. The core is the architecture, and GraphCast from Google DeepMind is our benchmark for modern MLWP.
GraphCast is, a cutting-edge, global deterministic model. That means it predicts a single future state. And it's built on this specialized architecture called a graph neural network.
GNN.
GNN, right.
So for those of us who are less familiar with deep learning architecture, why a GNN? What is it doing differently than, say, a traditional convolutional network, which looks for local patterns in a grid?
A GNN is designed to handle data that's structured as a graph, where information flows through nodes and edges. Think of it like a dynamic social network. The atmosphere is naturally a graph.
Hmm.
Every location influences every other location through these complex flows of energy and moisture.
Okay.
So GraphCast uses an incredibly elaborate multi-mesh strategy to capture this reality.
Elaborate is an understatement. Based on the sources, I mean, the input state alone is enormous.
It is. The model covers a 0.25-degree grid globally, which is over 1 million distinct grid points.
1 million points.
And at each one of those points, it takes in a staggering 227 variables.
227.
That's 5 surface variables plus 6 atmospheric variables like wind and humidity, but repeated across 37 different pressure levels. Is the atmosphere described in an incredibly high dimension?
That's the initial state. So how does the GNN process all that?
That high-dimensional input is first encoded. It's mapped into a node representation onto a specialized multi-mesh graph. This graph is mathematically derived from recursively subdividing a regular geometric shape, the icosahedron.
Right.
They start with a base mesh, M0, which has only 12 nodes, and they refine it through 6 steps, which culminates in M6, which has over 40,000 nodes.
That's a heavy dose of geometry. Can you give me an analogy for the listener? Why bother with this complex multi-resolution structure? What's the point?
Think of it like a spiralized camera lens that has 6 different zoom settings, but they're all active at the same time.
Okay.
Traditional models often have to pick one resolution.
Mm.
But the atmosphere has processes that operate at vastly different scales.
Mm.
A global jet stream that's an M0 or M1 scale affects the formation of a local thunderstorm, which is down to the M5 or M6 scale.
So the multi-mesh structure is the core innovation of that 16-layer deep GNN processor.
Precisely. It allows the GNN to perform what they call message passing, simultaneously across all 6 resolutions. The model learns from fine-grained local details at M6, while it's also capturing the coarse global patterns at M0 at the exact same time.
So it's learning how local information propagates globally and how global patterns influence local weather.
Exactly, which is how energy and moisture propagates in the real atmosphere.
Mm.
It gives the AI this holistic view that is both zoomed in and zoomed out.
And crucially, this GNN isn't trying to predict all 10 days at once.
No. GraphCast uses an autoregressive generation process. It iteratively applies the model to predict the next 6-hour state from the current and the previous state. So it's rolling out the forecast over time.
It's taking 6-hour jumps.
6-hour jumps. And one important detail from the training, they specifically weighted the loss function, giving 2-meter temperature the highest weight, a 1.0.
Why that variable specifically?
It means the model prioritizes getting the surface temperature right over less crucial variables, which is really clear engineering choice. They're prioritizing application value.
So we have a benchmark model that is architecturally brilliant and ridiculously fast. But speed is useless without skill. We need to see how that complexity translates into actual predictive power against the systems they're trying to replace.
Right. And when these AI models first entered the public conversation, the headlines were, and rightly so, dominated by their deterministic skill. This claim that they could produce a single highly accurate forecast that was better than the ECMWF's best single-run prediction, the IFS.
So they weren't just saying they were catching up to the gold standard. They were claiming they were exceeding it on metrics like root mean square error or RMSE. You provided data on Pangu-Weather and GraphCast leading this charge.
That's right. Pangu-Weather, for instance, was trained on decades of high-quality ERA5 global reanalysis data. We're talking 39 to 43 years, depending on the variable. So when it's initialized with similar high-quality data, both Pangu-Weather and GraphCast routinely claim stronger deterministic results than the operational IFS.
And that must have been the moment the scientific community realized this was a genuine threat to the established order.
Oh, absolutely.
And we can see that superiority quantified in specific high-stakes events, like hurricane tracking.
The analysis of Hurricane Florence is a really powerful illustration of the rapid progress here. Earlier versions of AI models, like the initial forecast net, showed significant deviation after the hurricane made landfall. It just failed to maintain an accurate trajectory over land, which is a very complex environment. However, ForecastNet V2 showed marked improvement. It was tracking the hurricane eye, which they defined as the location of minimum mean sea level pressure, with much greater accuracy. They're quickly learning how to handle these extreme localized phenomena.
But the real test, in my opinion, is how they fare when you pit them against real-world observations, not just training data. You cited a 6-month evaluation using ground truth data from Italian Seriati station.
And this evaluation is key because it uses real measurements from the ground, from SONOP stations, for essential variables like wind speed and 2-meter temperature. The findings showed that GraphCast generally achieved accuracy that was comparable to the IFS. But the key nugget of insight here wasn't just the raw score, it was the stability.
Tell us why that stability over time is so important for an operational meteorologist. What does that mean in practice?
So GraphCast demonstrated greater stability over the medium range, so specifically between 24 and 48 hours out. In traditional NWP, errors tend to increase relatively steadily as the forecast time lengthens.
Right, it gets worse over time.
It gets worse. In this test, when the traditional IFS errors tended to increase, GraphCast showed a slower degradation in its predictive accuracy. And in some cases, its RMSE and mean absolute percentage error, the MAPE, even decreased relative to the IFS, suggesting it maintained its coherence better than the physical model.
That's fascinating. If the ML model can maintain its coherence better in that 24 to 48-hour window, that's buying forecasters invaluable time to make decisions about high-impact events.
It is. But we have to pivot quickly to the fundamental truth we mentioned earlier. The atmosphere is chaotic.
Right.
So deterministic forecasts, no matter how skilled they are only half the story. And maybe the most dangerous half at that.
Right. The chaos inherent in the atmosphere is why we need ensembles. The butterfly effect ensures that small initial errors grow exponentially, which means predicting a single future state is eventually meaningless beyond, say, a week or so. You need a swarm of predictions to quantify the uncertainty.
And this is where the second generation of AI weather models introduce these powerful generative architectures to create the ensembles. GenCast, developed by Google DeepMind and ForecastNet-3 or FCN3 from NVIDIA, are really leading this shift to probabilistic forecasting.
GenCast in particular uses diffusion models. Now, most listeners probably associate those with image generation, creating realistic photos out of noise. How does that technique apply to weather prediction?
So diffusion models are generative. They learn by iteratively adding and then reversing noise. When you apply that to MLWP, they solve the crucial problem known as blurring.
What exactly is forecast blurring?
Imagine you ask an AI to predict a picture of a cat 10 days from now, but it's not exactly sure where the cat will be.
Okay.
If it averages all the possibilities, the resulting image is just blurry. It's mathematically correct in that it minimized the average error, but it's physically useless. Traditional models train purely on minimizing deterministic errors, like mean squared error or MSE, tend to produce this blurry average forecast over time.
So it's effectively becoming an ensemble mean masquerading as a deterministic forecast?
That's a perfect way to put it.
Yeah.
The model is hedging its bets spatially, which masks the real intensity of the features.
A blurry hurricane is not a useful forecast.
Not at all. So diffusion models, by reversing that noise, force the prediction to be spatiotemporally coherent and sharp. They manage to maintain physically consistent power spectra, which means the output looks less like a blurred average and more like a plausible, high-resolution physical state, even if the model doesn't know precisely which of the possible states is the right one.
And the performance leap here is undeniable.
GenCast, using this diffusion architecture, consistently outperforms ECMWF's Operational Ensemble Prediction System, the ENS.
That's right. And it's measured using these key probabilistic metrics that reward both accuracy and uncertainty calibration. The main one is the Continuous Ranked Probability Score, or CRPS.
CRPS.
So if you're not familiar with the term, just know that CRPS is how we score the quality of an ensemble forecast. It severely penalizes ensembles that are both wrong and overly confident.
So too sharp.
Right, too sharp. But it also penalizes ensembles that are too blurry or too uncertain.
And GenCast beats the traditional gold standard ensemble on this crucial metric.
It does, across 15-day global forecasts, and that includes metrics like Breyer scores for extreme events. And the speed is phenomenal. GenCast can generate a full 15-day ensemble trajectory in around a minute on a single cloud TPU v4.
A minute.
That efficiency opens the door to generating ensembles with hundreds or even thousands of members, which would dramatically improve how we quantify uncertainty.
And GenCast isn't the only one pushing the speed frontier. FCN3, ForecastNet-3, brings its own set of astonishing speed gains.
FCN3 is another ensemble forecasting model. It's built on a transformer architecture, and it explicitly respects spherical geometry. It computes a full 15-day forecast in just 60 seconds on a single NVIDIA H100 GPU.
So same time, basically.
Right. But when you look at the raw efficiency numbers, that represents an 8x speedup over GenCast and a remarkable 60x speedup over the traditional ECMWF ENS system.
60 times faster than the traditional gold standard ensemble.
Yeah.
That is why we call this a paradigm shift. What makes FCN3 so much faster?
Part of it is in the underlying transformer architecture's ability to efficiently handle long-range dependencies across the globe. That's combined with highly optimized deployment strategies on modern hardware. Critically, SCN3 also addresses the blurring issue by retaining stable predictions and accurate power spectra, even at very long lead times. They've tested up to 60 days.
Wow.
This makes it highly competitive for subseasonal forecasting applications where speed and maintaining that physical sharpness are essential.
Okay, we've established the speed, the accessibility, and now the superior skill, both deterministically and probabilistically, at least according to these key metrics. So what's the catch? Because the history of science suggests that when you gain 4 orders of magnitude in speed, you usually pay a pretty significant price in fidelity somewhere.
You've hit on exactly the right question. The catch is that these MLWP models, while they are excellent emulators of the historical data we feed them, sometimes fail at the deepest, most fundamental level. They fail to adhere to the physical principles that govern atmospheric chaos and motion.
And this brings us right back to the famous butterfly effect. Let's explain what this means in practical terms for predictability.
The butterfly effect, mathematically, means that small amplitude initial condition perturbations grow extremely fast initially. Theoretical considerations and traditional NWP models all predict this rapid initial growth, and this fast growth is precisely what sets a fixed fundamental limit on weather predictability.
The theoretical maximum window you can forecast accurately.
Exactly. So if a model doesn't capture that initial rapid error growth, it's incorrectly suggesting an atmosphere that is far more predictable than it actually is.
And what did researchers find when they rigorously tested these leading AI-based models against this phenomenon?
They found that the AI-based models completely failed to reproduce this rapid initial error growth rate.
Completely fail.
Completely. This structural deficiency would incorrectly suggest an unlimited predictability of the atmosphere. The AI models only start agreeing with the physics-based simulations when the initial perturbations are already large phi, comparable to the level of uncertainty we already have from satellites and weather balloons.
That is a profound scientific failure, even if the daily forecasts look good. It suggests the AI model hasn't learned the underlying physics of chaos.
Right.
It has only learned the general behavior of the atmosphere based on historical data that already contains large errors.
Precisely.
So what is the operational danger of that failure?
The danger is complacency. If the model says the atmosphere is more predictable than physics dictates, forecasters might become overconfident in a deterministic outcome beyond, say, the 5-day mark. It suggests that the AI is, in essence, averaging out the chaos rather than genuinely simulating it.
And that structural smoothing aligns with other observed spectral discrepancies, right? The blurring issue again.
Exactly. ML models often show reduced forecast variability at smaller spatial scales. They smooth out the detail, and they fail to show the signature drop in energy at synoptic scales. This drop is crucial. It's the physical signature associated with the chaotic loss of predictability in the medium range, around 3 to 5 days.
So by progressively blurring, models like GraphCast and NeuralGCM make their deterministic outputs look smoother and less variable than the real chaotic atmosphere.
It's like their beautiful, sharp forecasts are actually cheating by resembling an ensemble mean, which is always smoother than reality. It effectively masks the true chaotic nature of the individual forecast members.
And beyond the chaos problem, there's the fundamental issue of fidelity to the underlying governing physics. This is particularly visible in how they handle subtle atmospheric movements.
Yes, take the ageostrophic wind problem.
Okay, let's define that simply because it's highly technical, but it sounds absolutely essential to weather.
In the mid-latitudes, where most of the world's weather happens, air tends to flow in a balance between the Earth's rotation, the Coriolis force, and pressure differences. That balanced wind is called the geostrophic wind.
Okay.
The ageostrophic wind is the difference between that theoretical balance and the actual wind we observe. And crucially, the ageostrophic winds are the engine of active weather.
So active weather convergence, divergence, vertical motions that lead to storms and precipitation, it's all intrinsically linked to getting the ageostrophic wind right.
Yeah.
If the model misses that ageostrophic component, it misses the storm's formation.
Precisely. And we saw this flaw in the analysis of a leading deterministic model like Pangu-Weather. While Pangu-Weather produced plausible, if somewhat smoothed, broad-scale geopotential patterns, it got the big picture pressure systems, right? The intensity and spatial distribution of the crucial ageostrophic motions.
The engine.
The engine and the implied vertical motions were often much less plausible than the NWP comparison.
So the machine learned the general structure of weather, but it missed the subtle high-intensity dynamics that were driving the actual severe weather. What does that look like operationally?
It looks like a flash flood that wasn't predicted or a severe wind event that was significantly underestimated. The model got the general flow right, but it missed the energy convergence that turns general flow into a dangerous storm.
And this wasn't just Pangu-Weather.
No. Similar issues were seen in ForecastNet and GraphCast forecasts. It proves that simply learning from data doesn't guarantee adherence to these non-negotiable physical relationships.
Which means researchers have to actively engineer these models to adhere to these laws. They have to put these computational guardrails on the output to prevent non-physical results.
Exactly. A simple yet essential example is water quantity. A model like ForecastNet 3 predicts quantities of water vapor-specific humidity, total column water vapor, that physically cannot be negative.
Of course not. You can't have negative water.
Right. But when the model is optimized purely for statistical accuracy, it can mathematically spit out non-physical negative values.
Which makes no physical sense at all.
Zero. So FCN3 uses a once continuously differentiable spline function to smoothly clamp those water channels to the physically plausible range of 0 to infinity. They have to hard-code physical reality into the learning process to stop the AI from giving us imaginary negative water.
Let's talk about arguably the most high-impact failure point for MLWP, predicting extremes. Because if the AI is trained on historical data, how can it possibly predict an event that is historically unprecedented?
That's the core struggle. ML models struggle profoundly with extreme values because of two related issues. First is just the scarcity of training data for rare events. Hurricanes, major floods, severe heat waves. They don't happen often enough for the model to learn robust, generalized rules for them.
So if you're training on 40 years of data, and only 2 of those years featured a certain kind of severe storm, the model simply hasn't seen enough examples to learn its structure.
Precisely. And the second issue is a fundamental weakness of machine learning: extrapolation. If your system is trained primarily on historical data where the maximum temperature was, say, 100 degrees, it has a very difficult time confidently and accurately predicting a record-breaking 115-degree day.
Even though the laws of physics allow for it.
The laws of physics allow for 115, but the AI's training data doesn't fully support it. This leads to underestimation or instability, and it forces meteorologists to rely heavily on NWP systems for high-impact extremes.
And beyond these performance limitations, there's the fundamental issue of the black box when dealing with these complex, multi-layered deep learning models. How can operational meteorologists who need to make life-saving decisions trust a prediction if they can't trace the physical path that led to it?
Interpretability is a major barrier for operational adoption. It's a core tenet of meteorology to understand why a storm is forming. You can't dispatch emergency services or issue mandatory evacuations based on a system that simply says, "Trust me, the numbers worked out."
So what's the solution?
Researchers are tackling this aggressively through physics-informed solutions, PINs and explainable AI or XAI techniques.
I found the solution that leverages a mathematical equivalence between different types of architecture fascinating. It sounds like they used math to literally open up the black box.
They did. Researchers leveraged the equivalence between transformer architectures and graph neural networks on complete graphs. By viewing the model in this specific mathematical light, they could reinterpret the attention weights.
Which are normally just internal computational metrics used by the AI.
Right, but they could reinterpret them as quantified spatiotemporal physical influences.
So instead of the model just saying, there will be a storm in 3 days, the attention weights can now show that the prediction of the storm was most influenced by a large influx of tropical moisture from a specific region, which was interacting with a pressure gradient moving eastward.
Exactly. The model's internal decision-making process suddenly becomes readable in physical, meteorological terms. This allows the multi-head attention mechanism to disentangle atmospheric processes at multiple scales, capturing local influences, mesoscale dynamics, and synoptic circulation patterns.
So this breakthrough directly addresses that accuracy-interpretability trade-off. It enables improved performance alongside actionable physical insights for the forecasters.
That's the goal.
It sounds like the future isn't about one system triumphing over the other, but about designing systems that force AI to respect physics, leveraging the speed of the machine without losing the rigor of the science.
That is precisely where the research is converging. The hybrid model approach. The sheer speed and the growing skill of AI is too valuable to ignore, but the physical rigor of NWP cannot be abandoned. especially given the fundamental failure of current AI models to correctly model atmospheric chaos.
And the prime example of this successful bridging of the gap is NeuralGCM, which was developed in partnership with the ECMWF itself, the organization responsible for the gold standard NWP system.
NeuralGCM is a key hybrid model because it integrates machine learning directly within a traditional general circulation model, or GCM. You can think of it as having a two-part brain. It uses a differentiable dynamical core, which is the hard-coded physics foundation. It solves the large-scale dynamical equations for momentum and mass.
Okay, so that's the traditional physics part.
Right, but the second part is a neural network-based learned physics module.
So it's still running the fundamental core physics through the dynamical core, but the complex, messy processes that require massive computational effort in traditional models, things like cloud formations, radiation, and precipitation, those are being outsourced to the much faster neural network.
That's a perfect description. Those subgrid scale processes, known as parameterizations, are computationally expensive and notoriously difficult to model accurately with pure physics alone. The AI learns from historical data how these processes typically behave, providing a fast, sophisticated estimate that maintains physical plausibility, and then it feeds that information back into the slower, more rigorous dynamical core.
And the performance of this hybrid approach seems to validate the strategy.
Absolutely. NeuralGCM's ensemble model, even at a 1.4-degree resolution, has been shown to outperform previous state-of-the-art models for 5 to 15-day forecast accuracy. It really rivals the ECMWF ENS.
How much better?
In fact, one source states that NeuralGCM's ensemble accuracy was better than the ECMWF ENS 95% of the time for 2 to 15-day forecasts.
95%. That's a massive endorsement for the strategy of using AI to accelerate and refine the traditionally hardest parts of the physics model.
It is, and the hybrid approach also shows massive promise on climate timescales.
Right.
When running long-term climate simulations, NeuralGCM showed dramatic improvements over atmosphere-only physics models. For a 40-year temperature prediction, NeuralGCM's error was one-third that of conventional models' 0.25 degrees Celsius error versus 0.75 degrees.
A third of the error.
By accelerating the physics parameterizations, it stabilizes the long-term simulation, making it far more accurate for climate studies.
Okay, we've covered the global medium-range models. Let's shift now to the sharpest end of forecasting. Kilometer scale and regional predictions. This is where AI needs to prove it can predict damaging severe weather.
This is the domain of convection-allowing models, or CAMs. They're essential for predicting things like thunderstorms and mesoscale convective systems because they explicitly resolve convective dynamics at very fine scales.
Often 3-kilometer resolution, like NOAA's Operational High Resolution Rapid Refresh System, the HRRR.
Exactly, the HRRR system in the U.S.
So given that ML models struggle with extremes and rare small-scale events, can AI really compete here?
It can, through sophisticated emulation. Stormcast is a generative diffusion model that was specifically designed to emulate NOAA's HRR. Stormcast is autoregressive, and it predicts an enormous amount of detail. 99 state variables with dense vertical resolution, especially in the atmospheric boundary layer, all at that kilometer scale.
Did it actually manage to learn the fine-grained dynamics needed to predict severe weather elements like cold fronts and updrafts?
Yes, and this is truly impressive. Stormcast successfully learned kilometer-scale dynamics, including physically realistic features like convective cluster evolution, moist updrafts, and the structure of a cold pool morphology.
Which is that cold air that rushes out ahead of a thunderstorm, right?
Yep.
And that's crucial for triggering new storms.
Exactly. And critically, it maintained realistic power spectra across multi-hour forecasts, achieving comparable or even higher skill than HRR forecasts for short lead times, up to 6 hours, particularly for variables like radar reflectivity.
So this confirms the potential of ML to emulate even the most demanding, highest resolution physics models.
It does.
Another clever approach is physics-guided downscaling, where AI is used not to replace the physics, but to fill in the detail, but with constraints.
That's the PhyDL-NWP framework. It incorporates parameterized physical dynamics, using a technique called latent force modeling, directly into the deep learning models. This ensures physical plausibility and allows for continuous resolution-free weather downscaling.
What does resolution-free mean in this context? How does that work?
It means you train the model, and then during inference, you can generate super-resolution data at arbitrary granularity. You don't have to specify, I want 1 kilometer resolution. You can ask for 500 meters or 2 kilometers, and the model generates it based on the physical laws it has learned, all without needing coarse granular input.
So it's like generating a high-resolution map of a storm without needing a low-resolution original because the physics is guiding the detail generation.
Exactly. And this physics guidance provided a significant accuracy improvement, up to 7.18% over RMSE for specific datasets, proving that physics can act as a powerful constraint and guide for the AI's creativity.
Finally, let's look at the long view. AI for climate modeling. If we're running thousands of years of simulation, efficiency isn't just nice to have, it's non-negotiable.
And the efficiency gains extend dramatically into climate research. Consider the Deep Learning Earth System model, or DLRVA. It was originally trained for only one-day forecasts, yet it surprisingly succeeded in capturing seasonal and interannual variability over centuries.
And the key benefit here is the accessibility it brings to climate research, which is usually gated by supercomputer access.
Absolutely. DLESIM simulated 1,000 years of the current climate in just one day, using less computing power than conventional methods. This achievement radically lowers the barrier to entry, putting complex, long-term climate experiments, previously limited to a handful of national labs, within reach of researchers who simply do not have access to national supercomputers.
That's a massive boost for global climate science collaboration.
It really is.
And the model quality was validated against severe weather events over those long timescales, right? It wasn't just fast, it was good.
Yes, DLESIM was shown to simulate tropical cyclones and atmospheric blotting events, those stubborn atmospheric ridges that deflect weather systems and cause severe regional weather, just as well as the leading physics-based models. This validation ensures that the model isn't just fast, it's robust enough for serious climate impact study.
That is a powerful summary of where we stand. Let's bring this all home and identify our key takeaways from this. This deep dive has shown us a revolution in progress. The emergence of these MLWP models like FCN3 and GenCast has fundamentally shaken the field of weather forecasting. They've achieved comparable or even superior skill to the traditional gold standards, the IFS and the IFS-ENS, but with an astonishing speed advantage up to 60 times faster inference.
And this speed translates directly into the democratization of forecasting, offering critical socioeconomic benefits globally by making these high-resolution predictions accessible outside of major national centers. However, we have to remember the central tension. The reliance on data-driven patterns, without the full enforcement of fundamental physical laws, means these models still struggle with inherent, non-negotiable issues of atmospheric chaos, of true error growth, and guaranteeing physical consistency.
Especially related to the complex dynamics of ageostrophic winds.
Exactly.
The current trajectory seems pretty clear. The future belongs to the hybrid approach. Models like NeuralGCM integrating the speed of AI for difficult parameterized processes while keeping a differentiable dynamical core for physical rigor are the clear path forward. That seems true for both short-term weather and long-term climate modeling. We've seen AI models like Stormcast successfully emulate NOAA's HRR to produce physically plausible kilometer-scale convection, and DLESIM simulate 1,000 years of climate in a single day.
And this rapid convergence highlights a crucial, often overlooked, dependency. The key to the success of all of these new ML models is that they're trained almost entirely on the historical forecast data and reanalysis that was generated by those traditional physics-based systems.
So data sets like ERA5, which is the product of decades of ECMWF's NWP runs, and the output of high-resolution models like HRR.
Yes. In short, the AI is learning its foundational rules from the homework that was handed in by the physics simulators.
That's right.
So it raises a very important provocative question for you, the listener, to mull over as you see these models become operational. If these foundational NWP models were completely phased out in favor of faster, cheaper AI emulators, would the next generation of AI models eventually train on their own, subtly degraded output, creating a self-referential cycle that slowly loses touch with the actual governing chaotic laws of atmospheric physics?